I'd like to welcome everyone to the Designing a Horizontal Architecture for Constellation Data Processing, our Q1 webinar, hosted by AI Solutions and the Space Products team. I'll be your moderator, Christopher Ulrich, Space Products Account Executive here at AI Solutions. I'm also going to be joined by Regis Ghani, also a Space Products Account Executive, and he will be monitoring your questions in the meeting chat and during the end of this webinar, so make sure you folks stick around for that. If we jump to the next slide here, just some logistical items before we begin. So all attendees will be muted and our cameras will be off for the duration of the webinar. We will be recording the webinar for future reference and playback on YouTube. After today's presentation, we will follow up with a PDF of the slides via email. And at any point, you may use the chat to post questions during the webinar. And at the end of the presentation, we will host a Q&A session to answer them. If we jump to the next slide, we've got a very exciting presentation today for everyone, led by our very own Scott Lowe. So Scott Lowe is a Meridian product manager leading the design, development, and evolution of Meridian, a large-scale flight dynamics ground system supporting mission-critical space operations. With a foundation in the creative arts and extensive experience developing ground systems across multiple systems, he brings a unique perspective to complex system architecture, emphasizing the clarity, usability, and human-centered design. His work focuses on transforming intricate aerospace challenges into intuitive, scalable solutions that strengthen the human-machine experience. Without further delay, I'd like to reintroduce Scott and turn it over to you. Please take it away, Scott.
Thank you very much, Chris. Like Chris said, I'm Scott Lowe, and I have been working at AI Solutions for over a decade now. And I have a lot of experience building out different ground systems and across different missions. And one of the biggest things that we're seeing across the board with space missions that are going up is a lot of not just 10 or 20 spacecraft kind of constellations, but thousands of spacecraft constellations. And so what we're seeing, especially with the shift in technology, is that we need to update our processes, our flight dynamics processes, to be able to handle that kind of large scale system, right? So if you're familiar with AI Solutions at all, you are familiar with the fact that we develop flight dynamics software. And we've been doing it for a while, over 30 years now. And back in the days that we used a chalkboard or calculators, our founders of our company decided that it would be really great to take all of the great algorithms that we develop as flight dynamicists and build them into our own proprietary software that we could use to package up the flight dynamics that we run every day and deploy them into satellite operations centers. And not only do we build that software, we also are users of that software. So it's, we're a services and product company, so we build products, but we also go on contract into the Mission Operations Center, and we use the flight dynamics tools that we build to do the flight dynamics tasks that you would need to in an operations center. We typically work alongside a flight operations team and something like a mission planning team to make sure that a spacecraft is in orbit, that everything is flying safely. And this is what we are doing day in and day out, and this is what I've been a part of in all the ground systems I've worked on. But I wanted to take a specific look at a specific operational scenario, and in this case, we'll take a look at maneuver planning to try to do a little bit of a compare and contrast between how did a legacy mission, a single spacecraft mission, take this approach versus how would we do it for a constellation that needs to be doing maneuver planning for potentially thousands of spacecraft. All right, so in this scenario, we would have the mission planning team say, hey, FDS, we've got a situation, we really need to plan a maneuver. So the mission planning team will give our flight dynamics team a maneuver target input, and that'll have all of the information that we need in order to target a maneuver and get the spacecraft to fly in the way that we need it to fly. So we'll generate that maneuver, and that'll turn into what we call a maneuver report that we hand to the flight operations team. That flight operations team will say, hey, this looks great, let's go ahead and fly it. And then as the spacecraft is flying that maneuver, we collect telemetry, and that gets fed back into the system so we can do some calibration, measure performance, and make sure that the maneuver was successful. So this is a great process. This has worked for, thousands of space missions in the past, but there's one big problem, which is that this process is not scalable. If we have 1,000 spacecraft, you can imagine having all of these people in the room, coordinating files, sending things from computer to computer, doesn't work. So to take a look at what we do to solve this problem, which is a combination of automations and flight dynamics, let's take a look at the details of how we would do a typical maneuver planning session. So if you want to do a deep dive into maneuver planning, there's lots of, I believe we have a few talks on that. But at a high level, what we're doing is we're taking in those maneuver targeting inputs and we're generating that maneuver report output. Remember, that's what we generate to hand to the flight operations team to actually fly our spacecraft. We use FreeFlyer, which is our high fidelity flight dynamics tool. And it's important to remember that with a high fidelity planning tool, the high fidelity data is high fidelity. It can be massive. It can be a lot of data, and it can take a long time to crunch through those numbers, even though it's a high performance tool. So each one of these steps, maneuver targeting, orbit propagation, and maneuver validation, each one of these can take some time, and it can generate a lot of data because, again, high fidelity. Now, of course, when we're running this process, we are looking for constraint violations. We're making sure that as we're flying our maneuver, that we're staying within our control box and making sure that other requirements are being met. And if one or more of those requirements aren't met, we adjust those input parameters. We run the whole thing again. So again, the big takeaway here is that this is a great process. It's worked for a lot of spacecraft, but as you know, if you've ever flown, done flight dynamics in a ground system, this process can take time. High fidelity data can be resource intensive. So what do? Well, like I said, we have maneuver planning software that we've developed for a long time, and it does a lot of really great things to make sure that the spacecraft is doing what it needs to be doing. And then when we take that and we apply it to a large scale scenario, we start to see a couple patterns emerge. So when you're flying a lot of spacecraft, the flight dynamics are typically very well understood. You're not doing stuff that's super complicated individually, but the complication comes in when you have a lot of spacecraft that are all potentially interacting with things simultaneously, right? So you can imagine if you have a high fidelity solution and you have to calculate thousands of maneuvers, that translates to large scale resource requirements, and not just compute resources, but human resources. So how do we scale? How do we make sure that this is a mission that's always available in case you have a data center or a piece of data get dropped in one particular calculation? How do you make sure that the whole constellation stays flying? So let's take a look at how we would take a constellation maneuver operation, something that typically would have 1,000 spacecraft, and run it through a maneuver planning task. So you can remember for each spacecraft, we have to target and propagate, check their constraints, and potentially repeat a number of times. So here's some pseudocode that gives kind of an example or a flavor of how we would do this with something like FreeFlyer, right? We would say, while we have a constraint violation, run maneuver targeting. That might take 5 minutes for a spacecraft, propagation, validation. And this all produces highly accurate results. So, just as a back of the napkin kind of calculation, let's say that after running this, it takes about 10 minutes to run and generates about 100 megabytes worth of data per maneuver. Multiply that times 1,000 spacecraft, and you can see where the problem comes in, right? We have 7 days worth of CPU time that we spent and about 1 gig of resources. So, of course, we can take this to the cloud, right? The land of infinite compute resources, and just run this in parallel, right? Well, there's some problems with that approach too. So you are able to parallelize things in the cloud, which is great if your budget allows for it, but parallelizing things only shortens your end time, right? So if each maneuver planning task, if each one can be handled totally separately and doesn't need to do things like share state, then you could get in theory, if you had all 1,000 of these maneuver planning tasks all running simultaneously, you could get the completion time down to 10 minutes. But as far as the invoice comes in at the end of the day, you're still paying for almost 7 days of CPU time, and you're still generating a gig of data that you have to manage in that cloud instance. And this is for every calculation. It's not just one that you have to do. So depending on your ConOps, you could be doing this multiple times a month, multiple times a week, hopefully not multiple times a day, but who knows? We're trying to prepare for the worst case scenario here. So what we do is we use advanced automation. And I guess what does that mean, right? So really, when we say advanced automation, what we're talking about is breaking everything down into smaller units of work. So taking that kind of monolithic approach where we have one big mission plan that's executing a whole maneuver plan and breaking each piece down into smaller components. Once we break those smaller components down, we can organize each step as data pipelines. And we do that, and this is what I'll get into in a little bit to kind of explain what event-driven paradigms are. We break these data pipelines down into steps that are called producers and consumers, and then we're able to orchestrate those producers and consumers into what we call compositions. And this is all event-driven paradigms that allow us to essentially run a flight dynamics mesh in the cloud. All right, so to talk about the architecture that we use and give a little bit of a deeper dive into how we're building this kind of system, we'll start with the container management platform. So if you're not aware, container management platform is what is essentially our ticket to ride in the cloud. So being able to deploy things as containers is what allows us to natively export things into the cloud. We support lots of different container running technologies like Kubernetes and Podman and Docker and things like that, as well as proprietary technologies like AWS's container ecosystem like ECS or EKS, Azure, Google Cloud Platform. All of these technologies all support containers. So the first thing that we do is we take all of our great flight dynamics that we've been developing for 30 years and we package them as flight dynamics containers. And then, of course, to be able to use those containers, we need what's called cloud configuration templates. So configuration templates essentially allow you to choose as a system admin how you deploy all of those flight dynamics containers into a cloud management platform. So on Meridian, if you think about it from a high level, really Meridian is a collection of those custom flight dynamics containers containing the software that we use to run our flight dynamics, along with cloud configuration templates that a system admin can go and custom tailor to fit their environment. Now, the last piece of the puzzle, which is really what allows us to perform an event-driven architecture as opposed to more of a legacy approach, is something called an autoscaler. So technologies that you can think of are Keda or Native. There's a lot of different technologies on the market that will allow you to do this. But what it effectively gives you is the ability to do something that we call event-driven load balancing. So to talk a little bit more about that, let's take a look at an example. So if we have a Constellation maneuver operation, you can imagine that as a bunch of maneuver planning tasks, however many that you need to fly. And of course, because you're on this auto-scale container native, cloud native infrastructure, you have what's called auto-scaled resources. So in Meridian, we're just leveraging tools that are already available in your cloud system to basically be able to auto-scale those resources up and down on demand. And so basically, as you're running these maneuver planning tasks, this generates what we call task back pressure. So this is all of the volume of data and CPU time that you need in order to plan these individual tasks. And then Meridian manages that task back pressure by feeding it into the auto-scaled resource system. And this is essentially our pressure control system. You can think of this as like a flight dynamics specific load balancer. So to get even more in-depth example and to show you kind of how we do things at, again, this is, the cloud can be really deep, but this is still a 10,000 foot view here. Let's take a look at how we deploy things. So we have a number of different containers within Meridian that are always on. We call these our API services. So there's like an event management system, API routes that you can hit, and a task management system that's working together with other components to make sure that those tasks are executing on time, that if there's a constraint violation, that things are restarted correctly. And then the last thing that we have is a number of different resources that form what we call a data stream or a cloud buffer. So you can think of this as being just a giant data pipe that can exist across multiple data centers. The details can get a little bit tricky, and it's way too long of a topic for this talk. But the big providers like Uber and Netflix and some of the larger scale data companies that we have all use the same approach of having a very, very large data mesh that they use to handle all of their data. So that way, if a data center goes down, the data stream stays up. So let's say that we have that same Constellation maneuver operation, and we have an operator submit it to Meridian and say, hey, I need to fly this, this large scale set of maneuvers. That operation would go into our API route. The API route would work with our task management system. The task management system would then work with the autoscale infrastructure. Again, this can be anything, any cloud platform that you're running on. And then the task management system is coordinating to turn on these task containers. These are all running concurrently. They're all load balanced. And so they're able to split that processing horizontal. And then as the containers are running, they're generating information, which is both pushed and pulled through this data stream cloud buffer. And then, of course, we have monitoring systems in place to make sure that everything is being generated correctly. So when we say that we're breaking things down into smaller chunks and handling them in a data pipeline, this is effectively what we mean. And this is what allows us to be the Netflix of flight dynamics. So to talk a little bit more about events, remember we have those event stream containers that are up and running. These are things that exist across data centers. We have multiple containers that can be running in a data center at any time, and all of the traffic is essentially load balanced. So you can imagine a single message is a pretty tiny piece of data. But for this example, what we're going to do is take a look at how that message is fed into a task. So we have a running task, and this can be very simple. This can be a couple lines of code. This can be something that's way more complex, like hundreds and hundreds of lines of code or thousands of lines of code. But we don't want this task to be very big. We want it to be a small data processor. So we design this task so that it can subscribe to messages that come in on a specific subject. And then this task will run and process the data that comes in, and it'll do it as fast as possible. And again, we take kind of a Linux philosophy of do one thing and do one thing well. And then it'll produce more data on another subject, so subject B. So this is essentially the paradigm that we use for everything. And this might look a little bit familiar if you're familiar with pub sub patterns from different systems, but the big thing is that this is not a simple event queue or pub sub paradigm. This is a full event streaming platform. And really the benefit that this gives us is it allows us to produce a high volume of data, but also stay online consistently, right? So like if you have a data center go down, or you have computers in your data center go down, it doesn't stop the flow for us. It just degrades performance for a temporary time until we can get those resources back online, but everything stays operational, and so does the Constellation. So again, you can think of this as a pressure control system. So you imagine you can have hundreds or thousands of tasks all running simultaneously, all reading and writing data back and forth to this event stream. And then what you have is as tasks turn on and off. So like if you have 10 tasks and then all of a sudden you have a flight dynamics job that needs to run 2,000 tasks, we can communicate with the autoscaler and say, hey, add resources. So add physical hardware that you have backed up and ready and available to run these tasks. But then also, as the tasks are increasing pressure by producing events, we can also make the autoscaler aware of increasing resources based on those produced events. So the key takeaway here is that as the tasks turn on and off, and as more and more data comes in and out of the buffer, you can turn on or turn off resources as you need. So to take a look at how this works with the Constellation maneuver operation, which we should all be familiar with by now, we have our API services that are ready to receive this event, right? This operation request. We have our event stream in our cloud buffer ready to handle the data load. We give the API that same maneuver operation. And the first thing that gets produced is that maneuver subject. So you can think of this as the mission planning team handing our flight dynamics team a task, and the inputs, the data in that task gets published onto our bus. And then, of course, we have a maneuver targeter that is running and ready to receive that information and starts processing that immediately. And as it's running, it's generating target result subjects. So this is the whole maneuver targeter is able to look at this new input that's coming in and says, okay, here's what we need to produce. It pushes that to the cloud. Of course, for each maneuver that we do, we're going to publish a new topic, and the orbit propagator is going to pull that in and then generate a predictive orbit. And then, that orbit is going to be pushed back to the cloud. And then we're going to validate everything that we're doing as that data is coming in and going out. And of course, if there's a constraint violation, the way that we have this set up makes it easy, because we can just have the maneuver validator check. And if there is a violation, we just throw an error log and we say produce another maneuver subject with altered inputs, and then the whole process starts again. So rather than having like a software defined loop, this is a loop that's defined through task composition. And then, of course, the really nice thing about doing things in this way is that as an FDS operator, you can be paying attention to any piece of data you want, or potentially complex queries where you can be looking at data in aggregate. And what this allows for is a really robust way to get introspection to any point in the system. So this is a bit more of a deep dive. I'm not going to go into every single step here. Feel free to send me messages, and I'd be happy to talk your ear off if you want to get into this, though. This is an example of an event-driven task. And really what you have on the left is the maneuver targeter producing data. The orbit propagator is configurable, so it can consume different subject patterns. And so that way, as data is being produced by the targeter, that subject pattern can be picked up by the code. Our code can then use that data to propagate forward and publish that data. And again, we can configure how that data gets produced on the cloud. So that's not something that our code needs to define ahead of time. We can have an operator come in and say, well, this data is what's really important for us to be publishing, so we're going to publish using this subject and this information in this format. And then, of course, any other downstream service can pick up that information and run with it. So this is what we call compositional automation. And again, it's all based on this idea that we have an event stream available. Our operators can write their own task scripts. And not only can they write their own scripts, what they can do is they can design those scripts into composition. So, not just one script working by itself, but multiple scripts that can be instantiated hundreds or thousands of times. So here's an example composition. Typical composition could have an FDS task that's processing some data, reading events in and producing data out. We could have a data sync in here. So a big point to note about an event stream or cloud buffer is that you don't need to always have all of your data saved all the time. Actually, for the most part, it's important that you don't save all of your data all the time, because you're potentially generating, gigabytes per day. So or potentially even more. So you use data syncs to store in performant ways, specifically only the data that you need, and that way you can configure where that data lives long term. And then, of course, we want to keep our operators in mind. In this composition, we have a complex query, which is basically turning data into meaningful information, right? It's looking at lots of disparate data points that are potentially coming over this cloud buffer and creating a complex query. So again, compositional automation patterns are what allow us to really create these pipelines. And this is really similar to things that we've done really for the last 50 years with Unix systems, right? We take things that we break down into small components that each do that one thing well, and we push those out and we put them into different patterns that we can use to filter that data in different ways. So we're designing these data pipelines, but all of our content can be flight dynamics specific. There's a lot more information here, but again, if anybody's interested, I'd be happy to talk more. So as a last step, let's take a look at what we're doing with our Constellation orbit operation, right? So we have to do maneuver targeting, orbit propagation, and maneuver validation. You can see that for maneuver targeting, we can scale up our flight dynamics task just based on how much volume of data we're producing through targeting. Orbit propagation, we might be able to propagate a significant number of orbits in batches. So it might not be that our flight dynamics tasks are necessarily one-to-one with the number of spacecraft. We could potentially be looking at this data and saying deterministically that we're going to run a flight dynamics task that processes all of the spacecraft in a single plane as opposed to individually to potentially save bandwidth, make things more efficient. And the same goes through for validation. Validation could be potentially a really quick process. Just every time there's a subject that's published that has some piece of data that needs to check, there's 5-10 second validation operation that goes through and makes sure that everything's fine, and then publishes the results back to the data stream. And again, the big benefit in the end is that as we're breaking these patterns down into smaller chunks, we can have operators pay attention to just the pieces that they need to, and the whole system can be handled on different bandwidths. So the same way that you can stream a movie from Netflix using like a low bandwidth connection or a high bandwidth connection, we can do the same things. We can see things in real time, and in the end, our operators get access to a high availability, large scale system without having to install large software on their desktop or really have to do anything in particular. They just open a browser and they can view all of the events as they stream in. So again, thank you for taking the time to sit here and listen to what I think is as a 10,000 foot view into a really much deeper topic. Be happy to talk in any more detail about any of these topics if you're interested. And thank you very much.
Thanks, Doug. That was informative. Yeah. So anyone in the chat, feel free to ask any questions. And I see we actually have a couple right now. So Scott, first question being, can Meridian provide COLA/conjunction assessments?
Yes, absolutely. So that's actually one of those things that we've been looking into a lot is when you move to like a large scale horizontal architecture, each of the tasks that you're running in a container can be paired with different requirements for how you can do that. So for instance, if it's important that you process a large amount of data really quickly, you can leverage technologies like a GPU or an advanced processing system. You can allocate resources on demand. So we recognize that not every situation in flight dynamics calls for a GPU. Most don't. But when the opportunity arises, we can play games with architecture and spin up the types of resources that we want. So that's one of the really exciting things that we've been looking into very recently with COLA in particular.
Another question from the same person is, does it offer maneuver planning templates or optimizations? For example, can I say I want to null out my inclination on this geo satellite, or I want to plane match and perch 100 kilometers negative intract this RSO with the ability to assign a max amount of time for the maneuver set/plan to achieve my parameters?
Yeah, I believe you can. So that's one of those things that I know we build all of our technology on top of the capabilities that are built into FreeFlyer. So a simple answer to that is if you can do it in FreeFlyer, you can do it in Meridian. It's just Meridian gives you the customizability to really kind of tweak that to your specific mission. One of the things that I always kind of gloss over when I talk about this stuff is how, custom tailored every maneuver plan is for each mission. Every mission handles it, potentially very differently. And so that's why we build Meridian to be customizable, is that, if you can do, a maneuver plan with one spacecraft, you can apply that in lots of different ways to things like, different orbital planes or different constellation groups. So there's, long story short, there's a lot of different ways that we can configure it to match that scenario. And that's an awesome question that I wish I had more time to really kind of dive into each detail on.
Question. What kind of some of the configurable constraints I can configure? FOV 15 degrees solar / Earth exclusion window, maneuvers should not exceed 10 meters per second, etc.
Yeah, so I think there's, I don't have a full list in front of me of all the different constraints that you can add, but again, this is Free Flyer is a scriptable platform. So if you can come up with the logic for how to apply those constraints and those requirements, then you can write that script into existence. So yeah, yes, again, that capability is there, but I would love to sit down and kind of talk more about, how we can add those fields to be able to, meet those specific parameters.
Another question. Can I define the fleet flight rules that tells the system to intelligently plan station keeping maneuver to keep them in their lanes for the entire constellation?
Yeah, so that's an awesome question because one of the things that we have to do a lot of is manage state between different calculations that we're doing, and so one of the biggest bottlenecks that you can run into in like a large scale system is when you have to share state between multiple running containers. So in general, I can tell you how we handle that, which is that we essentially have our tasks when they run their atomic operations that essentially externalize the data across that streaming mesh that I was talking about. I think, yeah, Ragesh, were there any other details of the question that I might have missed there?
Good. I have another question for you. If you're ready for the next one. Will it be available on classified environments?
Yes. We are flying operationally across a number of different missions. We are deployed into both low security and high security environments and classified environments.
Another question. Is the tool accessed through a cloud-based web portal only, or will there be a desktop app similar to Free Flyer?
Yeah, so Meridian is, I think of Free Flyer as being the desktop app for flight dynamics for doing, individual, like if you're an analyst and you want to go in and you want to sandbox out like a flight dynamic scenario, like you're using Free Flyer to do that. Meridian is the server approach that we do to deploy our flight dynamics. And Meridian is what you as an operator would use. So right now we have a client server paradigm that Meridian can be deployed into a closed, it can be deployed on bare metal. It doesn't actually need to be deployed in the cloud. You can deploy it on, a single machine if you wanted to do that. We have, browser capability. There's something called the PWA, which is allows you to run the interface as if it were a desktop application, and we handle our UI design as if you're using a desktop application. But in general, Meridian is designed to fill the gap between the flight dynamics algorithms that need to run and the rest of the ground system infrastructure that needs to happen in order for your mission to fly. But long story short, we can deploy Meridian anywhere. You could deploy it on a laptop. You could deploy it in a bare metal server. You can deploy it in the cloud. We handle all things in the same way.
And then we have a question from our friend Michael Volley. Do you have any recommendations for Free Flyer scripting patterns to fit well within this sort of architecture?
Yeah, so the big thing is write procedures and make them small so that way you can break those up. I think that's the biggest thing that we have done as a company as we've gone from legacy ground system operations, single spacecraft kind of operations to modern cloud systems is the best thing you can do to buy off any kind of technical debt is take large mission plans and break them down into small chunks that do one thing and do one thing well. That was sort of why I was really, that was a big part of this talk is that was a huge way that we were able to realize and adapt our flight dynamics to systems that needed to be distributed. And there's good ways to do that too. There's techniques for doing that. But happy to talk more on that.
Yep, and then we have follow-up from Shane, who asked us for 6 questions. He has a follow-up for number 1 on COLA. Do we need to provide the states for all of the RSO objects we want the COLA run against, or can Meridian run against the full space track catalog?
So, right now we're looking at how we would be doing COLA for an entire constellation or subset of the constellation against the entire catalog. It becomes a performance, calculation problem, and it's not necessarily that we can or can't do it. It's just how does that information or how does that calculation get distributed across nodes. So we do have a design approach for that specifically, but yeah, so it's interesting because it's not necessarily a capability that is baked in or not baked into like our flight dynamics code. It's more how do you take that code and then deploy it into an operational environment. But yeah, we have some good techniques there.
Follow up on another question you answered. FigVar scripting tools are very powerful, but I think there could be some value in creating a more intuitive interface, such as a planning wizard that covers some of the use cases without needing to create the free file logic with trial and error to achieve the desired function.
Yeah, that's actually one of the most fun things about working on Meridian has been that I've gotten to see the sort of flight dynamics or otherwise software engineering mistakes that I've made in the past, like looking back on the different ground systems that we've stood up. You get to see how it might have been right at the time, but there's ways that we can optimize and improve that. So what we have in Meridian now is like a great set of mission plans and procedures that we use on every mission that we fly. Again, every mission has like some really custom tailored, like maneuver planning is wildly different for every mission that we fly, right? So we always create these different paradigms for that. But what we've ended up with over the years is a collection of really amazing flight dynamics scripts that can handle a lot of different situations. And because they've been battle tested, we've been able to like simplify them down into specifically, what's the best way for this algorithm to get the job done.
And Shane, for your third question on pricing and how it works, after this webinar, we'll have someone from the sales team reach out and actually work with you on setting up a meeting time, go over pricing and more on-hands question about Meridian, showing you a demo. Cool. Then I see someone else typing right now, so I'm going to wait to see if they have a question.
Yeah. And I guess reduce on that last topic too, with demos. I love running demos. I love pulling up like the Meridian interface and showing off sort of what we've been able to build. And I wish I could give this talk at the beginning of each one of the demos because it does kind of give you an idea of what's happening under the hood. Because with the Meridian UI, with a demo, you typically are seeing things from an operator's perspective. But a lot of what we do is put a lot of time and effort into sort of the ground system management, managing all of the different pieces that need to work together.
I'm going to give it another 10 seconds in case anyone else have any last second questions before we move on. Cool. So before you go, Scott, if you want to hit the next slide. Yeah, so I want to thank you all for attending today. We really appreciate your participation and collaboration. As a reminder, we will provide the recording and slides to all the attendees in the days ahead. We'll also post this webinar on our YouTube page. If you have any other questions on FreeFly or Meridian, feel free to reach out to us through email at sales@ai-solutions.com. Visit us on our website, freeflyer.com, or call us on the phone number on the screen. With that, this concludes our webinar. Thank you, everyone.